we'll look at simple probability, independent events, and mutually exclusive events. The key idea is this. On the SAT, probability is not just about calculation, it's about choosing the right idea for the situation. Probability questions on the SAT often look deceptively easy. The numbers are small, and the math itself is usually straightforward. That's exactly what makes them tricky. Here's the real challenge. The math is simple, but the situation is what matters. A small detail in the problem, like whether you replace a card after drawing it, or whether two events can happen together, completely changes which formula you should use. And here's where most mistakes happen. Students choose the wrong approach at the very beginning, then calculate perfectly, in the wrong direction. The math is correct, but the answer is wrong because the idea was wrong. That's why probability on the SAT isn't really about calculations. It's about recognizing what type of situation you're dealing with before you start solving. Probability questions on the SAT often look easy at first. The numbers are usually small, and the calculations themselves are not very difficult. That's why many students feel confident when they first see the problem. But on the SAT, probability is not really about the numbers. What matters most is the situation behind the question. A small assumption, such as whether one event affects another, or whether two outcomes can happen at the same time, can completely change which answer is correct. Many wrong answers on the SAT don't come from bad math. They come from starting with the wrong idea and then calculating correctly in the wrong direction. That's why, before doing any math at all, you need to pause and ask what kind of probability situation you are actually given. In this lesson, we'll focus on learning how to recognize the right probability idea first, so your calculations truly match the situation. Now let's look at independent events. Independent events mean that one event does not affect the other. What happens first doesn't change what can happen next. Look at this coin toss example. The first toss has a 50% chance of heads and 50% chance of tails. Simple enough. Now watch what happens on the second toss. Notice the label here, no effect. The probabilities remain exactly the same, still 50-50, regardless of what happened on the first toss. This is what independence means. The outcome of the first event does not change the probabilities of the second event. The two events are completely separated. Here's a common SAT trap. Students sometimes think that if heads came up first, tails is now due on the second toss. But the coin doesn't remember what happened before. Each toss is independent, starting fresh with the same 50-50 probability. So when you see a probability problem on the SAT, ask yourself, does the first event affect the second one? If the answer is no, you're dealing with independent events, and that tells you how to set up your calculation. Now let's look at mutually exclusive events. Mutually exclusive events cannot happen at the same time. If one occurs, the other cannot occur at all. Look at this diagram. Two circles, one for heads, one for tails. Notice there's no overlap between them. In fact, look at that X in the middle with the label, cannot happen together. That's the defining feature of mutually exclusive events. When you flip a coin once, you get either heads or tails, never both. The moment one happens, the other is impossible. That's mutual exclusivity. Here's a critical distinction for the SAT. Don't confuse mutually exclusive with independent. Independent events can both happen, they just don't affect each other. Mutually exclusive events cannot both happen, period. For example, rolling a 3 and rolling a 5 on a single die roll? Mutually exclusive. But rolling a 3 on one die and a 5 on another die? Not mutually exclusive, both can happen at once. So when you see a probability problem, ask, can these two outcomes occur at the same time in this situation? If the answer is no, they're mutually exclusive, and that changes how you calculate the probability. Now let's compare these two concepts side by side. When you see a probability problem, your first step isn't calculating, it's identifying the relationship between events. And there's a simple way to do this. Look at the left side, independent events. First question, can both events happen? Yes, they can. Second question, does one affect the other? No, it doesn't. The key characteristics. Events are separate, and probabilities stay the same throughout. Now the right side, mutually exclusive events. Same first question. Can both events happen? No, they cannot. Second question. If one happens, does the other happen? No, it's impossible. The key characteristics. No overlap, and one outcome completely rules out the other. This is the distinction that trips up many SAT students. These concepts sound similar, but they're fundamentally different. Independent events can coexist. Mutually exclusive events cannot. So here's your strategy. Before you calculate anything, ask the right question. Can both events occur in this situation? That one question tells you which type of relationship you're dealing with, and once you know that, the rest of the problem becomes much more straightforward. Here is a beginner practice question. A coin is flipped once, and a six-sided die is rolled once. Which statement is correct? Are these events independent, or are they mutually exclusive? Take a moment and think before choosing your answer. Let's look at this beginner practice problem. We need to identify the relationship between a coin flip and a die roll. The correct answer is A. The events are independent. Now let's break down why this is the correct answer. Look at the why section on the slide. There are two key reasons here. First, both events can happen. Think about this carefully. You can flip a coin and roll a die at the same time. There's nothing in the situation that prevents both events from occurring together. They can coexist. Second, one does not affect the other. This is crucial. Whether the coin lands on heads or tails has absolutely no impact on what happens with the die roll. Look at the images on the right. The coin shows heads and tails, and the die shows all 6 numbers: 1, 2, 3, 4, 5, and 6. The coin's outcome doesn't change any of those 6 possibilities on the die. Now, here's the key idea at the bottom of the slide, and this is worth remembering for every SAT probability question you encounter. Events are independent if both can happen and one does not change the probability of the other. That definition matches our situation perfectly. The coin flip and the die roll are completely separate events. They happen independently, with unchanging probabilities. Neither one influences the other in any way. So the answer is A. These events are independent. Let's try one more beginner practice problem. This one is very similar to the last one, but pay attention to how the probabilities work. Take a moment and see if you can figure it out on your own. Now let's work through the answer and explanation for this problem. The question asks, what is the probability of getting heads in A3? The correct answer is 1/12, written as the fraction 1/12. And here's the calculation. 1/2 times 1/6 equals 1/12. Now let's understand why this approach works. Look at the why section. There are two critical points here. First, these events are independent. The coin flip and the die roll don't affect each other. Getting heads or tails on the coin has absolutely no impact on what number comes up on the die. Second, because the events are independent, their probabilities multiply. This is the key calculation rule for independent events. Let's see this in action with the numbers. Look at the coin on the right. The probability of getting heads is 1/2, or 1/2. Now look at the die. The probability of rolling A3 is 1/6, or 1/6, since there are 6 equally likely outcomes. To find the probability of both events happening together, we multiply these probabilities. 1/2 times 1/6 gives us 1/12. And here's the key idea at the bottom that you need to remember for the SAT. For independent events, multiply the probabilities. This is a fundamental rule. When events are independent and you want both to happen, you multiply. Recognizing this pattern will make probability problems much more straightforward. Now let's move on to an intermediate problem. A bag contains 3 blue balls and 2 red balls. 2 balls are drawn one at a time, without replacement. What is the probability of drawing a blue ball first and a red ball second? Take a moment to study the steps on the right, and think it through. Now let's work through this problem step by step, using the structure of the slide. First, look at the answer at the top. The correct answer is 3/10, written as 3/10. You can see the full calculation here. 3/5 times 2/4 equals 6/20, and 6/20 simplifies to 3/10. Now let's move to the why section and understand why this method works. These events are dependent, and that's the key idea here. They are dependent because the first draw changes the contents of the bag. Since the ball is not replaced, the probabilities change after the first draw. Now look at the right side of the slide, and let's break it down step by step. First draw, blue. At the start, there are 3 blue balls out of 5 total, so the probability of drawing a blue ball first is 3/5. Second draw, red. 1 blue ball has been removed, so now there are 4 balls left. Out of those 4 balls, 2 are red, giving a probability of 2/4 or 1/2. Now look at the line that says, and means multiply. Because the question asks for blue first and red second, we multiply the probabilities. 3/5 times 2/4, which gives 3/10. And finally, here's the key idea at the bottom of the slide. For dependent events, you must update the probabilities after each draw. Without replacement, means the situation changes, and your calculations must change with it. Now let's try an advanced probability problem. A bag contains 3 blue balls and 2 red balls. 2 balls are drawn one at a time, without replacement. Given that the second ball is red, what is the probability that the first ball was blue? Focus on the outcomes where the second draw is red, and think carefully about what remains possible. Now let's go through the answer step by step. The answer is 3/4. And the reason it's 3/4 is that this is a conditional probability problem. Look at the why section on the slide. It says, given that the second ball is red, we only keep outcomes where the second draw is red. That is the entire idea of conditional probability. When you see the phrase, given that, you do not start by multiplying everything blindly. You first restrict the sample space. In other words, you throw away every outcome that does not match the condition. Here, the condition is, the second ball is red. So we only keep cases where the second draw ends up red. Now the slide says, there are two possible paths. Let's go through them carefully. Path 1. Blue right pointing arrow red. Look at path 1. First draw is blue, 3/5. That's because at the start there are 3 blue balls out of 5 total. Next, then red, after blue was removed, 2/4. This 2/4 is the crucial part where many students make mistakes, so let's say it clearly. We are drawing without replacement, meaning we do not put the ball back. So after drawing 1 blue ball first, the bag now has 4 balls left. And the number of red balls is still 2. So the probability that the second ball is red, given we already drew blue first, is 2 out of 4, which is 2/4. Now multiply along the path. Path probability. 3/5 times 2/4 equals 6/20. So the probability of the sequence blue then red is 6/20. Path 2. Red right pointing arrow red. Now look at path 2. First draw is red, 2/5. That's because at the start there are 2 red balls out of 5 total. Next, then red, after red was removed, 1/4. Again, we are drawing without replacement. So if the first ball drawn was red, then 1 red ball is removed. That means, on the second draw, there is only 1 red ball left in the bag, and the total number of balls is now 4. So the probability that the second ball is red, given the first draw was red, is 1 out of 4, which is 1/4. Now multiply along this path. Path probability. 2/5 times 1/4 equals 2/20. So the probability of the sequence red then red is 2/20. Now compare only the second is red outcomes. Now we do the conditional probability step. Look at the right side of the slide. It says, now compare only the second is red outcomes. Exactly, because the condition is, the second ball is red. So we keep only the 2 paths that actually end with red on the second draw. Blue right pointing arrow red, which is 6/20. Red right pointing arrow red, which is 2/20. Everything else is ignored. Now, among the outcomes where the second is red, the question asks, given that the second ball is red, what is the probability that the first ball was blue? So we are asking, out of all the second is red cases, what fraction of them came from the path that starts with blue? That's exactly what the slide shows next. So the conditional probability is 6/20 divided by 8/20 equals 6/8 equals 3/4. Let's interpret that in plain language. The successful group we want is blue right pointing arrow red, which is 6/20. The total group that matches the condition, second is red, is 6/20 plus 2/20, which is 8/20. So the fraction inside the restricted sample space is 6/20 divided by 8/20. The over 20 cancels out, leaving 6/8, which simplifies to 3/4. So the final answer is 3/4. Key idea. Now look at the key idea on the slide. It says, conditional probability means you restrict the sample space. That is the core rule. And then it says, when you see, given that, ignore all outcomes that don't match the condition, and compute the fraction within what remains. So here's the SAT strategy. Before you calculate, pause and ask, what does the condition force to be true? In this problem, the condition forces the second ball to be red. So we keep only the paths where the second is red, and within that smaller set, we find the fraction where the first ball was blue. That's conditional probability. And that's why the answer is 3/4. Let's wrap up this lesson with the key ideas you need to remember about probability. In any probability problem, your first step is to identify the sample space. Before you calculate anything, be clear about what outcomes are possible in the situation. Next, always determine the relationship between events. For independent events, one event does not affect the other, so the probabilities stay the same. For dependent events, the situation changes, and the probabilities must be updated. When you see the word "and," it usually means you multiply probabilities, but only after you've confirmed the events involved. And when you see the phrase "given that," You're dealing with conditional probability. That means you restrict the sample space first, and then calculate within what remains. On the SAT, success in probability is not about memorizing formulas. It's about understanding the situation, identifying what changes, and choosing the correct probabilities. If you get that process right, the math becomes straightforward.